Hi, my name is Eric Herkus, and I enjoy creating for entertainment and education. Today I want to introduce you to happyml and give you a basic tour of what you can do with it. I will point out that while it works, and there are some useful things you can do with it, it's not complete yet. I do hope that you can learn from it. That's one of the best takeaways that we could get, best outcomes. There is a lot here, and I take notes throughout. You'll find embedded in the code little details of things that I learned along the way, and maybe there are things that you will take away from that, and that would be really great for me. One of the things that makes happyml so special, and one of the reasons that I made it, was so that I could do something called quantization, 8-bit quantization, during training, not just inference. So there are many different machine learning frameworks out there that can do 8-bit quantization. The quantization is a fancy word that's basically an approximation. And it means that you use less memory. And the reason that you see these large language models that can only be done by certain big companies is because of the amount of hardware it takes to do training and to run them too, but also to do training. And you can take some of these larger models and run them, use them on less hardware with quantization during inference. That's the point at which you're doing your predictions. But the reason you can't generally predict using these frameworks with quantization is because if you take an estimate or an approximation and you multiply it by another approximation and you add another approximation to it, you end up with trash. You end up with something really bad. What I do that I think is special that ends up working, at least as far as I've been able to test, is that I will keep it. I use a CPU instead of a GPU. A GPU is your video card, or a TPU, which is a tensor processing unit, which is a specialized hardware that's used for machine learning. I use a feature of the CPU, which is different than the GPU, to do a series of complicated operations really fast. And I will keep those numbers in full precision while I'm in the process of doing it, and then save the approximation at the end. So instead of approximation times approximation plus approximation, I actually use real accurate number times another accurate number plus an accurate number to get a value that I then save as an approximation. And I can do that really fast, or fast-ish, with a CPU, because that's how CPUs work, is they do a series of complicated operations much better than a GPU, which does simple operations in parallel really fast. So what this all means is that you can train really large models using commodity hardware. It is not as fast as if you were to be training with specialized hardware. But if you are somebody who doesn't have thousands and thousands of dollars of hardware, or even millions of dollars of hardware to train some of these very large models or run them, it would make it possible to do something that you would otherwise not be able to do at all. It'll still be slower. It's not like you get something for free here. It will definitely be slower than if you were to use one of the other machine learning frameworks and have all the specialized hardware. But if you don't have all the specialized hardware and you don't have that sort of money laying around, this gives you the ability to at least attempt it. But again, being that it's slower, and some of these large language models, as an example, they have a lot of data involved. It would still be intensive. But what I hope this will do is it will do for machine learning what Linux did for operating systems and even the cloud. You think about Linux, what made it special was that it was this license agreement and that it worked with commodity hardware. You didn't need special hardware from Sun or from IBM, etc., to run it, and it allowed to work on basic commodity hardware that you could then get more commodity hardware, but commodity hardware is really cheap. That's the beauty of it. And we've seen some of that commodity hardware specialize a little bit in the cloud, but it's more or less still commodity hardware. It would work on your desktop machine, so you could do those sorts of things. That's what I'd like to see here. Now, you might say, Eric, I could still run PyTorch locally. Yes, you could, but the size of the models that you could train are relatively small in comparison to what we're talking about, the large scale models that really take a fantastic amount of GPU memory or TPU memory that most people simply do not have. It would be very, very expensive. And even if you were to try to pay for that in the cloud, which you could, it would be very expensive. And it's also very complicated to set up. So that's one of the things I am doing here is I'm creating the ability to do 8-bit quantization during training that otherwise you might not be able to do at all. And so making things possible. All right, I rambled on a lot about it, but that is what makes happyml. The reason I tackled it was to try to open this up. The final thing I want to do is make it accessible, and I've made a language spec that I haven't finished building. I've not been feeling well lately, so it's not quite done. But my goal is to create a SQL-like language that allows you to create models and train them very much like you might use SQL, and you don't necessarily have to have a deep machine learning background, data science background in order to be able to do it. That you could actually use these models and create them using plain text interface. And so you could imagine, even if you had a Python program or a Java program, etc., you could interface with this code without actually having to know all the details. It would pick sane defaults. It would, when trying to train, it would do some effort to figure out what was the right type of model to build in order to get the results that you're looking for. So a declarative approach, much like SQL. You don't need to know how databases work internally in order to use a database. You just have to understand some basic concepts. And that's what I would like to do here, is provide an interface that it does not require you to understand how to do data science in order to build a model that would allow you to make your own predictions or inferences. So yeah, that's kind of the gist of it. Let's kind of dive in. Let's talk about an example. And so this example that I want to show you today is an MNIST example. I don't actually know if I'm saying it right, but I think that anybody who's ever done any machine learning examples ever has used this data set. I should point out the README. There's a README here in the example folder, and it shows you where I got it off of Kaggle. This data set, it's basically a bunch of handwritten numbers along with what number it represents as data. So if we were to look at the data, the number 7 is represented by this image, and I have it as a CSV, so you can actually just look at the data. You can see each pixel is 0 through 255. So these are it's a grayscale image. It's a 28 pixel by 28 pixel image, and somebody took the time to label out what number does this image represent. So in this case, we have like 10,000 images or something like that here, I forget. So that is kind of our training set and our test data set. We'll talk about that a little bit more as we go, but the gist of it is that you can get a data set like that. There's a whole bunch of them out there. They're free on Kaggle. And that's one of the things I love about that, is that you can just go download them. There's a bunch of different data sets out there, and you could go build your own model. Today, our example is a convolutional neural network, CNN. Maybe you've heard about them. They aren't an exactly new concept. They've been around for a little bit, but they are fun because they are used to put labels on images. So this is a dog, this is a cat, this is the number 8, whatever. You could do things like that. So this example, we have handwritten numbers 0 through 9. We want to map them out back to data. So say you want to build a model like that. How would you go about it? Well, the first thing we need to do is define our labels. And in our case, we have the labels 0 through 9. And what we're going to do is we need to be able to encode and decode those. So these numbers, and they need to turn into sort of these arrays that look like this, right? And this is the number 0, this is number 1, 2, 3, 4, 5, 6, 7, 8. Right, this represents the number 8. Or this represents number 3. 0, 1, 2, 3. There's some technical reasons for this, but it works best when they say these labels were, instead of 0 through 9, they were cat, dog, monkey, seal, whatever. These text labels would mean something else. It would still get mapped out to an array like this. Oh, this is the most probable thing. It's most likely a dog, or it's most likely a cat. So that's how this works, is we have our categories. It happens to be numbers here. It's just text. We really could have any text there. All right. So that's kind of our category labels. It gives us an expected shape. We have 10 possible outputs. We're going to see down here, we have 10 possible our expected output. You think about this as like a three-dimensional, like a Rubik's cube. It's one cube tall. It's 1 cube tall. It's 10 cubes wide, and it's 1 cube deep. So it's basically an array. That's what that is. If you're a programmer, you know what an array is. It's a three-dimensional array, but we only are 10 wide. The given shape is we have an image. We look at our test data one more time here real quick, and it was a 28 by 28 pixel image, and it had a label at the beginning. So we said, oh, there's a header row. We aren't trimming the strings, and the expected value was at the beginning. So our expected value in this case was 7 for this image, 2 for that image. So it's the very first column, and there's only one column for the expected values. It was 28 by 28 pixels, and that's the gist of it. All right, so now we have a training data set that we've loaded in, and we have a test data set. In machine learning, you can have multiple data sets. Very commonly, you have a training data set, you have a test data set, and sometimes you have a validation set. A training set is what you're actually going to use the machine learning on to learn something. The machine will learn from the training set. The test data set is a unique data set that's not in the training set, so it's completely different images, and it's how we know whether or not the machine learning model learned anything. So the reason we don't want our test data in our training data is that if that test data was in the training data set, the machine might memorize those values. So we don't want it in there because this comes into a term called generalization. We want our solution to work for any image. So even if there's no data in the training or test, but I draw the number 1 on a sheet of paper, draw the number 5 on a sheet of paper, it should recognize that even though it's never seen an image of me drawing the number 5. And this is to help prove that our model is generalized. It works on any given set of data, and it's because our test data wasn't our training data set. There is another type of data set out there called validation set that is neither the training data set or the test data set, but is used to validate later. I did not use one in this example, and we're not going to really dive into that a whole lot here. Making a machine learning model using happyml is super easy, super quick. You say I want a neural network builder. You don't have to, but if you specify a model name and repo, we can then later on save it off to someplace. It will be saved off to our repo folder. And so you could save it and load it in later. If you trained a model, you ideally would probably want to save it so that you could use it without having to retrain it, because sometimes training can take hours, right? In this particular case, it took about 52 minutes the last time I ran this. We wouldn't want to wait around 52 minutes for it to relearn everything. We'd rather train the model, save it, and then we'll be able to reuse it later. And effectively, that model is this configuration right here plus whatever it learned, and that learning goes into a folder, and it just represents. I've got my own file format called tensor. It describes how each of these layers were set up. So what did it learn? And while that could be optimized a little bit, right now it's pretty legible. It works pretty well, and you could use that. So that's we defined those so we could save it later. You will see throughout here some activation functions. So this is ReLU, there's sigmoid here. Those they help determine how the signal moves between neurons in this neural network. You don't have to worry about a whole lot. ReLU is, though, a very super common one in CNNs, and sigmoid is also pretty common as an output function. We'll talk about it a little bit, but effectively its goal is to give us a probability. When I showed you these numbers up here, it's actually going to be a whole series of probabilities, 0.1, 0.2, 0.3, and it might look like, actually, let's tweak this a little bit. Instead of it being 1, say it's 0.8 here and 0.1 here. What this would be is it's saying maybe there's going to be one other 0.1 here somewhere because it's got to add up to 1. All right, so I'm 10% probable that this is really the number 0, 1, 2, number 2. I'm 10% probable it's number 4, but I'm 80% sure this is the number 8. So we only care that it's really it's the highest probability. It's 80% sure that it's that number. So that's what sigmoid does for us, is gives us the probability of each of the possible labels that it might be. That could be useful later on. Say we have a whole bunch that are nearly the same probability. We might take other additional actions after that to decide what to do about it, because maybe we're not sure. We could look at that to say, how sure are we that this is that number? But anyway, we're not going to. Finally, we tell our neural network builder to create the model, and we now have a model that we can then train. Let's see if there's other interesting things here to talk about. The input, we give it the shape from our test, our training set. We say, all right, this is what the shape of the data is. That shape was a 28 by 28 pixel image. We are going to apply a filter to it with a kernel size of 3. This is getting into convolutional layers, and I am not going to explain it in this video. That is something that is documented well on the internet. We could talk about it for a long time and why they're interesting, but effectively they're helping us identify interesting qualities about the image. So you think about if we send in our image, we might want to be interested in what sorts of shapes it picks out, certain curves, certain edges, other things. And this is going to help us do that. This middle node here is where most of the learning is happening. This is what's called a fully connected layer. And this fully connected layer, is where most of the learning is actually happening in the neural network. And then the output layer, which is right here. This is also a fully connected layer, but what's special about it is it's going to be that expected shape, and it is we create an output we can capture. We're basically telling the neural network, I want to capture what this produces when we're done. So we could theoretically have multiple outputs if we wanted to. Say you want to predict in chess, from example, the chess engine I built, you want to predict not only what the best move is, but you also want to predict what is the evaluation of the current position. Is this position a good position or a bad position or an even position? So you predicted 2 things with the same model. So in this case, we only have one single output, and that's the deal. We have to set, we have a default precision exit strategy. The exit strategy is when we go to train, what's going to happen is it's going to go through the training data set one time through, and then it's going to look at the test data set to decide how well did it learn. And it's got to decide, am I done? Have I learned enough? And the exit strategy is configurable. You can use I made 2 pre-built ones, a low precision exit strategy and a high precision exit strategy. The low precision one is not as stringent. It prefers to finish when it's good enough. Where the high precision exit strategy is going to keep training until it's very super precise, but you could wait hours, days, weeks to have it finished training. In this particular case, the default is low precision strategy, and you might go, oh, Eric, that sounds like that's not very precise. Even the low precision exit strategy is still pretty precise, and most of the time is good enough. There are some use cases, though, where you may need the high precision exit strategy. I built it just for those cases. I left a commented out bit here just so that you know they exist, but it will default off to low precision. Once it does that training, and it's going to alternate. It's going to go run through the training data set. It's going to try to learn as much as it can. Then it's going to go through the test data set to see how accurate, did I get the right answers when I look at the test data. If it did get the right answers and our precision's really good, it's going to go, all right, I can exit now. I'm done. And there's a couple of different rules that go into it. We're not going to get into them here, but you can configure it. You could build your own exit strategy if you wanted to. Whatever you need. And we are going to do it in batches of 4. So that means 4 images at a time we will do predictions on, and we will work through our whole data set. There is a whole topic about batch size. I'm not going to cover it right now, but for this one, we're basically trading off the speed at which it trains. So 4 at a time versus 1 at a time. We'll train faster if we do 4 at a time, versus precision to a certain degree, but it's not even that simple. It is actually a little bit more complicated than that, and I'm not really going to dive into batch size right here because, like I said, it gets a little bit complicated in rule making, and we don't really need to cover it for this example. Finally, all right, we got done training. After this returns, we get a loss. What a loss represents is we want a loss to be as low as possible. 0 means that we learned everything perfectly. We didn't get anything wrong when we did we checked our tests. We got everything right. In this case, when I ran it for 20 epochs, or it decided the exit strategy didn't exit for 20 epochs, and It took 52 minutes to get a loss of 0.0097. That's really good. So that's very close to perfect. It's not perfect. It would, if we got perfectly zero, that would probably tell us something's wrong, because that should not happen to get all the way to zero. But we want to get as close to zero as we can before we exit out. And that's good. So that's basically what loss tells us. Lower, it's not something that's easy to just equate to a percentage right. You couldn't say, oh, it was wrong 1% of the time. That's not what this represents. It's a lot more complicated than that. And there's different loss functions that we might use, and I don't really want to dive into them. But more or less, no matter what, we want the loss to be as low as possible. That's good. All right. And also, that's also part of the exit strategy, is it will figure out if the loss is going down, or if there are the situations in which the loss could start going up, and it will actually capture the best output that it got at whatever. So say I train, do an epoch, and then I do another epoch and another epoch, and it realizes that it's actually not learning anything more. Not only is it not learning, it's actually getting worse at the tests. It will go take the best epoch that it had when it exits. That's by default. You could theoretically set up the exit strategy to take the last one, even if it was worse. I don't know exactly why you would do that, but there's something called overfitting. It is possible to overfit, and so sometimes people will, to avoid overfitting, they will not take the best outcome. They will take the last one. But I think that for our purposes, taking the best one is generally good. And there are other things we can do about preventing overfitting, and overfitting is a whole nother topic that we'll cover maybe another time. Finally, we're going to go loop through our test data set one more time. I restart it because we've been using that test data set this whole time right here. And we're going to restart it so that it goes back to the beginning of it. And we're going to manually walk through 50 of them and just print them out for the sake of, oh, look, if we have the expected value that was in our output. It was supposed to be a 7. We predicted it was going to be a 7. Yay, yes. And then finally, this is just the loop. We're just going through, and then we'll print out our loss too, just for fun. If we were to save it, it looks like this. Save with, there's actually a number of different save functions. I have a save with overwrite, so that we can overwrite the existing one. We could actually have it save and not overwrite, and have it so you throw an error. Actually, instead of throwing an error, what it'll do is it'll put it in another location, because I figure if you spent an hour or 4 days saving or training the model, and then you had save and you didn't put overwrite, you'd probably be pretty upset if you lost all your work. So if you say save without overwrite, what it'll do is it'll save it off in another location if the file actually already exists. And then here I was just testing it out. I reloaded the neural network from scratch out of the save, and then did a test with it to see that it worked, and it did. And that's basically it. That's my little walkthrough. I know there's a lot of details I skimmed over, and hopefully we'll get to the point where we can make it as easy as this, where you specify your plan for how you want to train, what your goals are, and then based upon your goals, in a declarative fashion, much like SQL, it will be able to train, right? That's my goal. And I'm partway there. I'm still working on that, but I'm not done yet. But anyway, if you want, you can still use it as C++ and do exactly this. And hopefully this is helpful for you. So I really do appreciate your time getting this far. If you wouldn't mind, please like, subscribe, and if you could leave a comment on the video, that would also help the YouTube algorithm actually other people find this video. I would super duper appreciate that. And let me know what you think. Tell me if I said anything wrong, if I made any mistakes, if you had other thoughts, if you'd like to see more. Yeah. All right. Thanks a lot. I really appreciate you.